Section, we want to look at rate laws and reaction orders. So let's consider a simple reaction where A forms B. All right, and we're going to look at two different graphs for possibilities of A forming B for different reaction orders. One thing that's really important to note, and it says it way at the bottom, so maybe it doesn't seem that important, is rate laws are not dependent on stoichiometric coefficients. They must be determined experimentally. And we're going to learn a little bit later on in this chapter about mechanisms of reactions, because it may not be as simple as A instantly forms B. There may be some intermediates, C and D, that have to form along the way, which is why rates can't be determined by stoichiometric coefficients. They must be determined experimentally. So let's look at these two different graphs. All right. In the first case, we have concentration of A and time. So if this were a zero order reaction with respect to A, the only reactant, okay, the rate has to be determined on the reactant, not the product, because the reactant is what's reacting. If it's zero order with respect to A, then as the concentration of A decreases, okay, over time, it's a constant rate. Said another way, this is a line. Now let's say that it's first order. Well, if we look here, at the beginning, we have relatively a lot of A, and at the end, we have relatively little A, right? Because this is the concentration of A on this axis, so lots of A, a little bit of A. So the rate of the reaction slows as A gets used up. This is first order, N equals 1. What about for a second order reaction? So for a second order reaction, it's the same as a first order, except more extreme. Okay, so as the concentration of A decreases, the reaction gets even slower and slower and slower because there's a greater effect. So at the end of the day, we can write this rate expression, rate equals K, concentration of A, to some power. And that power will either be 0, 1, or 2. Note that if it's 0, then this wouldn't be in the rate law at all, because A to the 0 would just be 1. So we wouldn't write that. Now let's look at it from a different perspective where we have it written as rate laws. Here we have the rate and the concentration of A. Note over here we had the concentration of A and time. These are completely different graphs. So let's look at a zero order. Well, if A is 0.2 molar, this is how fast the reaction goes. If A is 0.6 molar, this is how fast the reaction goes. It doesn't matter what the concentration of A is, the rate goes at the same. The reaction rate is the same. That's because, as we just talked about, concentration of A to the 0 power is just rate equals K in this case. It doesn't matter what the concentration of A is, the reaction proceeds at the same rate. Now let's look at first order, the red one. If A is 0.2 molar, it goes at this rate, all right, somewhere around 0.003. If A is 0.4 molar, it goes at double that rate, which is somewhere around 0.006. And if A is 0.6 molar, which is 3 times this, okay, it's somewhere around 0.009. So as the amount of A increases, the rate increases, and we get this linear relationship here. What about second order? Well, second order, we have a squared effect. So if we go from 0.2 to 0.4, we double the concentration of A, but we actually make the rate 4 times as much. So let's say that this is, I don't know, what is a quarter of that? 5 times 10 to the minus 4 molar, which is about a quarter of 0.002, and we increase the concentration of A to 0.4, we get 4 times the rate. If we triple the concentration, we get 9 times the rate. If we make the concentration 4 times as much, 0.2 to 0.8, we get 16 times the rate. So the rate law is extremely useful because the rate law tells us how much faster will the reaction go if we change the concentration of one of the reactants. In this case, there's only one reactant. The other thing that the rate law is useful for is, well, how is the reaction going to slow down as the reactant gets used up? So for a zero order reaction, the reaction will not slow down as the reactant gets used up. But for a second order reaction, the reaction will slow down dramatically, all right, because there's a squared relationship as the reactant gets used up. So this gives you a little bit of an idea of the rate law. Unfortunately, the math to calculate rate laws is not super straightforward. So I'd like to spend a little bit of time going over some examples of that. The first type of question that we have is looking at a rate law that is given to us, where we're not actually trying to find the rate law ourselves. I'm going to switch over here to the camera. What can we glean from this information? So in this case, we have x plus y yields z. And we're told that the rate equals k, concentration x, concentration of y squared. Note that it's not x plus 2y yields z. Okay? This is just x plus y equals z. One question we could be asked is, what is the overall order of this reaction? Well, as we just talked about, this would be first order with respect to x and second order with respect to y. So we could say this is 1 plus 2, or overall third order. The truth of the matter is, third order reactions are relatively rare, but we could say in this case, the overall reaction order is third. Note, again, that it's not the stoichiometric coefficients. This is determined experimentally, and we'll do that in a minute, but that's the harder question, so we'll do that second. It says, what happens to the rate if the concentration of x is doubled? Well, we just said that this reaction is first order with respect to x. So if it's first order with respect to x, if the concentration of x is doubled, the rate of the reaction will also double. What happens if the rate of the concentration of y is doubled? All right, so if y is doubled, then there's a second order with respect to y. So this is going to be 2 squared, which is 4 times faster, or if you prefer, quadrupled. Okay? And it says, what happens to the rate of the reaction if x is tripled and y is doubled? So if x is tripled, it's going to go up 3 times. If y is doubled, it's going to go up another 2 squared times, because y is second order, so we have to square it. So 2 squared is 4 times 3. So this reaction is going to go 12 times faster. Okay, I guess I should write the word. 12 times faster if we both triple the concentration of x and double the concentration of y. So the rate law is very useful. If we care about how fast a reaction goes, okay, we can use the rate law in order to manipulate the situation so that it works in our favor. But finding the rate laws is a bit of a pain in the neck. And we'll talk a little bit later in the next section about the integrated rate law and a way to find rate laws from integrated rate laws. But in this section, we're going to talk about finding the rate law for x plus y yields z. We'll assume this x plus y yields z is a different x plus y yields z than the previous one. And what we're going to do this is we're essentially going to do 3 trials. All right, we have 2 reactants, and the minimum number of trials that we can do is 3. So let's look at our trials. When we look at our trials, what we're looking at is the relationship between the variables, the initial concentration of x and the initial concentration of y. So let's look at the trial 1 and trial 2. In trial 1 and trial 2, we keep x constant and we change y, and we see what happens to the initial rate of the reaction, which maybe we measure by spectroscopy. In trials 2 and 3, we've doubled the concentration of x, but we've kept the concentration of y constant, and we look at what happens to the initial rate of the reaction. So by making the table in this way, we minimize the variables, right? Because concentration of x is not a variable here, and here concentration of y between these 2 trials is not a variable. If we can isolate the variables and do a bunch of math, we can be able to figure this out. Before we start by trying to figure this out, let's write the general rate law for this reaction. And the general rate law for any reaction is going to be dependent on the reactants. So rate equals k, concentration of x to some power that I'm going to call m. I don't know that. Concentration of y to some power that I'm going to call n. So this is the general rate law for this reaction. Now I have a ton of variables, right? I do know rate, I do know the concentration of x, I do know the concentration of y, but I don't know k, I don't know m, and I don't know n. So how am I going to solve a problem where I have 3 variables? The truth is, you're not, okay? You can't just plug in one of these trials or just do one trial and solve all of this. It's not possible, which is why we did 3 trials. So let's look at trying to find m. All right, the first thing we're going to try to find is m. In order to find m, I need to compare trials where m changes and y doesn't change. So specifically, I need to compare trial 2 and trial 3. Okay, why did I pick trial 2 and 3 to find m? Because I care about the concentration of x related to m. The concentration of x changes, it doubles, and the concentration of y remains the same. That's how I decided. Now for trial 2 and 3, I want to fill this rate law out for the variable that I know, variables that I know, and leave it blank for the ones that I don't know. So rate, I know rate for trial 2, okay, it's 0.017804 equals k, I don't know k. Concentration of x, I know, 0.200. For clarity, I'm not going to put the variable in there, or the unit in there, molarity. I'm just going to leave it as 0.002. Raised to the m power, I don't know m, that's still a variable, times the concentration of y, I know, 1.000 molar, to the n, I don't know n. So I used trial 2 and I filled out the things I know. Rate, concentration of x, and concentration of y. Repeat for trial 3. I know the rate of trial 3. 0.071395 equals k, I don't know k. Concentration of x, I do know the concentration of x. It's 0.400 molar. Again, I'm leaving out units for simplicity. And I don't know m still. I do know what concentration of y, 1.00 molar, and I still don't know n. So I have now filled out everything that I do know for trial 2 and trial 3. And again, I picked trial 2 and trial 3 because x changes, and I care about x because I'm looking for m, and y does not change. Now, how am I going to mathematically get rid of some of these variables? Well, what I'm going to do is I'm going to divide these 2 equations. All right, I'm going to divide the entire equation. Why do I do that? Well, the reason I do that is because a bunch of stuff cancels out. Specifically, k cancels out because k is on the top and the bottom, and k divided by k is 1, so I can cancel it out. And more importantly, or equally as importantly, 1 to the n over 1 to the n cancels out. Rewriting. 0.017804 divided by 0.071395 equals 0.200 to the m divided by 0.400 to the m. Okay? So I have now found these found an equation with a single variable, m. Now I can do something with this. Specifically, I can find the value of m. First, these are both numbers. So since these are both numbers, I can just plug them in my calculator. When I divide these 2 things, I get 0.2494. So I simply divide those 2 numbers, and I get this value. Equals, you can rearrange this as 0.200 over 0.400 all to the m power. This is mathematically allowed. All right. Now, how do I find the value of m? Well, in order to do this, you may first notice that 0.2 divided by 0.4 is a half. So one further step of simplification is I could put 0.2494, okay, equals 0.500 to the m power. In order to find the value of m, we need to take the log of both sides. So the log of 0.2494 equals the log of 0.500 to the m. Note that now that I'm using the log, or the log base 10 of this thing, I can bring this m outside. It's no longer an exponent, it's now a multiplication factor because I've taken the log. So the log of 0.2494 equals m log 0.500 divided by log 0.500, and you'll find m equals the log of 0.2494 divided by the log of 0.500. When I do that math, I find that m is 2.003. It needs to be a whole number, which is approximately 2. It needs to be an integer. Okay, so this is how I've found this. Let's look at this from a practical perspective. I have doubled the concentration of X, and this rate is 4 times this. From a practical perspective, I could have, just looking at this without doing all this math, figured out that m is 2. That being said, you can't always just look at it, because if this went up by a factor of 3.8, right, and then this was a square of 3.8 squared, you might not see it, all right? So it might not be easy to see, but in this case, because the numbers are relatively straightforward, you could see it without doing all this math. Now, what I would suggest you do is that if you see how to do this, try to do the same thing to find n. All right, I'm going to continue the video where I find n, but I would suggest that you try to do that. So the next thing that I want to do is I want to find n. And just for the simple reason that there's no space, I'm going to find n separately over here. So rate, again, equals k, concentration of x, which I now know is squared, okay, concentration of y to the n. All right. Now, since we still don't know k, we still can't just plug in one set of values because we still have 2 variables, k and n. So we essentially have to do the same thing over again. If you wanted to leave this as m and this is n, it's not going to make any difference whether you put this in as 2 or whether you leave this as m. So how do I decide which 2 trials that I want to compare in order to find n? Well, n is related to y. So I want trials where y changes and x doesn't. And if I look at trial 1 and 2, the concentration of y between trials 1 and 2 is doubled. And the concentration of x between trials 1 and 2 is constant. This is perfect. This is the exact thing that I want. So I'm going to pick trial 1 and trial 2 to compare. Now I'm going to, just like before, fill out everything I know. I know rate for trial 1. 0.008814 equals k is still a variable. I do know concentration of x. It is 0.200 to squared, or if you want to leave it as m, it doesn't matter. All right. I know concentration of y, 0.500, but I don't know the value of n, so I have to leave that as a variable. Again, I have 2 variables, k and n. Now, I repeat for trial 2. So, the rate is 0.017804 equals k, still don't know k. In this case, the concentration of x is the same, 0.200, all right, still squared or still to the m, it doesn't matter. The concentration of y is now 1.000 to the n power. Now, if you remember what we did before, how did we get rid of these variables? Well, what we do is we divide these equations. What cancels out? Well, in this case, k cancels out, and the 0.2 squared cancels out. All right, or 0.2 to the m, if you like, cancels out. So this is what's left. 0.008814 over 0.017804 equals 0.500 to the n divided by 1.000 to the n, like that. All right, so simplifying, these two numbers, okay, can be divided. And these two numbers, it's half divided by 1. So that's obviously just a half, right? Any number divided by 1 is just the same number. So what I get is 0.500 to the n equals these two numbers divided by each other are going to equal 0.4951. Now, if you like, you can stop here. Why? Half to the n equals a number really close to a half. What does n have to be? It has to be 1, because any number raised to the 1 power is the same number. If you prefer, you could do the logarithms to find this. Take the log of both sides. So log of 0.500 to the n equals log of 0.4951. Again, now we're in exponent space, so this is no longer an exponent, it's a multiplication. So n log 0.500 equals log of 0.4951 divided by log 0.0500 divided by log 0.500, and you find that n is equal to 1.014, which is, again, rounded to the nearest integer, approximately 1. Now in these textbook type questions, these are going to come out perfectly. In the lab, maybe not, okay? But in textbook type questions, this is what you're going to find. So we can now rewrite our rate expression with the m and n included. So the rate is equal to k concentration x squared, because we found that m is 2 in the previous one, concentration of y to the 1, and we don't write the 1, we just leave it blank, because anything to the 1 power is the same number. So it's quite a lot of work, but these are the reaction orders with respect to these different things. So, because I don't have space, so I have this written over several times, all right, we have the rate here, we have the original equation, and now we have the rate law. What it asks us is, what is the overall order? I shouldn't have deleted this. So the overall order. Well, this is second order with respect to x, and first order with respect to y. So if it's overall, third order, 2 plus 1, which is third. All right, so you just add the exponents to find the overall order. The last thing asks us for the rate constant. And I apologize that I actually deleted the questions and not just the answers. So the rate constant. Well, we know the rate law. Rate equals k concentration of x squared concentration of y. If you're up to it, pause the video for a second and see if you can find the rate constant based on this. So to find the rate constant, we just pick any trial. I'm going to pick the first trial, but it doesn't matter which trial you pick. We now know all the variables except k when we plug in a trial. So we know the rate, 0.008814 equals k. Concentration of x is 0.200 squared. Concentration of y is 0.500 to the 1, or just 0.500. When we do this, we take this, we square it, and we multiply it by a half, which gives us 0.0200k, which equals 0.8008814. Divide both sides by 0.002, and we find that K is equal to 0.441. So, a lot of work, but we were actually able to determine the value of M, N, and K by doing simply 3 trials where we did them very carefully. We changed the concentration of Y in this case between 1 and 2 and not X, and between 2 and 3 we changed X and not Y.